speaker today, Ganesh Padmanabhan, is a CEO and founder of Autonomize, and a technology company applying trusted generative AI to power healthcare outcomes. This is the second part of his talk. So in part two, Ganesh will continue exploring what happened in the generative AI and large language model space, focusing on the healthcare use cases and opportunities. And so without further ado, please welcome Ganesh.
Thanks again for the opportunity. I really enjoyed the last interaction. A lot of questions. We didn't have enough time to touch through all the questions at that time. And you can see my screen as well, right? Quick, first off, thanks for the introduction. I'm founder CEO of Autonomize AI. Being in healthcare, building enterprise scale systems in healthcare, financial services, media and entertainment through multiple companies in the past. Had the fortune of actually being working in AI for almost a decade and a half right now. And it's funny, I was telling my daughter about how AI and how everybody's talking about AI and stuff. And it's like, I've been working on AI for 20 years. And she says, you must not be that good, because it's only now that it's actually gotten really good. So you had to work so hard to get it to where it is today. So excited about it, it's exciting times with AI and with this new generative AI and what large language models and foundation models really enable is quite fascinating. So previously, and Pradeep asked me to do a quick recap on what we talked about last time before I dive into a lot more deeper. So the emails he sent out has the recording of the last episodes, if you will. But here's a quick recap on what it is. I'm just going to spend 5 times on it. And then we'll dive a lot more deeper today. Not so much deep in terms of technology, but more like the use cases and what are the challenges. I mean, we never looked at the other side of this. How do you put this into practice? Where is it best used for? Is every problem a ChatGPT problem? Is every problem a large language model problem? We'll explore a lot of those kind of questions today. And hopefully at the end of it, I'll also give you a framework to think about when you're looking at your own efforts, within the Kaiser larger organization, within your own organizations, or, what does it really mean to build a UGPT, to win in the future, right? So previously, we talked about ChatGPT, how this one platform went from 0 to 100 million users in a matter of, weeks, if you will. And so it's over 100 million active users, about 10 to 20 million paid users. So it's just a fascinating story in product-led growth. But what really it signified is an evolution, right? And we went through this journey of now having the abundance of data to train these large language models. And if you guys any of you have been following Andrew Ng from Stanford who's the founder of Coursera, and a few other companies like Landing AI, and he coined this term of data-centric AI. So we're into this view of data-centric AI. And and without going too much into it, now there's a lot of data, and it is less about how do you tune and make a model and fine tune the parameters and stuff. It's about more data-centric workflows to make sure that your overall system performs better, right? So we're in that mode, given the standardization through transformer models and a lot of evolution that happened. So there's 3 things that really led us to what it is over the last decade, 2 decades. One is the abundance of data to train these hungry deep learning models. Second, most important thing is the cost of compute. It's not nearly as cheap. It's to use some of these really powerful large language models in enterprise grade right now, because it's going to be extremely expensive when you start using ChatGPT for doing summaries across 15 million members that you have in your platform. It's going to be very, very expensive. So, but still, it's a lot more approachable than it was before. And then lastly, the research interest, and the most researched topic over the last decade was deep learning and machine learning, right? And it also led to a lot more openness in researchers sharing their things, thereby democratizing access to these cutting edge algorithms. And one foundational underpinning is this transformer architecture, which is very widely used, which is open sourced by Google. And it is now kind of in a weird sort of way coming to bite them in the back, right? With OpenAI really challenging their search business. So what this moment in time really signifies is 3 broad capabilities. One is language, and I think language is historically, or ever since the human evolution, the development of the theory of intelligence starts with the expression and by using language as a way to express what you want, build stories and communicate and so forth. It was more than just a mode of communication. It's a way to reason and understand the world around us, right? And what we have now imparted with all these classical techniques that we actually added into large language models of understanding language, human language, the verbs, the nouns and stuff like that. But you add a lot of data that understands the very nuances of how humans communicate and talk and so forth. That really opened up a whole bunch of opportunities. So language is a core way. So being able to build these models that understand, communicate, can reason with language is a huge step. And it's not new as an approach. What is new was the abundance of the data, so you can understand all the wide varieties of it. The second building block was what we call the foundation models. And foundation models are nothing but, again, there's like you said, this move towards data-centric AI approach led to there are very few architectures today that are in deep learning and machine learning in general that are, very flexible yet very, very standardized. So what that does is a few things. One, it makes it easy for everybody to use it and then start building other things with it. It also makes it a little hard to change some of these like fundamental shifts to the architecture. So we might hit the limits of these architecture like transformers, which we don't know how to overcome yet, but we'll figure that out. But what that did was actually these foundation models made it available, made it easy for people to build on top of it. And that was also one thing that we saw with ChatGPT. And the last thing is my favorite thing, which is the human-machine paradigm, interaction paradigm shift, right? What ChatGPT more than anything demonstrated to the world is how do you very intuitively capture the imagination of millions or hundreds of millions of people around the world from different walks of life to interact with a common foundation model that's a source of intelligence, right? So what that does was a few things. One is if you had a search system in your enterprise that allows people to search for certain things, and you would just type a keyword and get the search response back. So even with Google was the gold standard in actually having people interact with knowledge and knowledge retrieval and information retrieval. Now the gold standard became just a more human way of communicating, using that language to communicate back to the users. You engage them, interact with them in a very human-like fashion, and that I think is an irreversible trend that we're going to see. We're going to start seeing this across everything we do in IT and outside. And then we talked about a little bit about, my friend Jeff Winter put this together, how the ChatGPT is a subset of this thing called transformer-based language models, which is a larger group, which is among this thing about generative AI. Generative AI is just the kind of AI that is about generating net new content, which is, inspired by the trained data, but actually net new that's produced out of zero, right, if you will. And then there is variation in autoencoder, there's GANs, and then there's ChatGPT. Was there a question, Pradeep?
No, I don't.
Okay, very cool. And then so this is a larger group of things. We're talking about a small, narrow thing, but it's fundamentally critical. But I'm going to, the rest of this presentation, we'll start looking at how all of this played together as well, right? We also talked about at a high level, generative AI in healthcare can be applied, in three broad different manners. And I have a lot of use cases later on to talk through. One is how do you reduce administrative burden and the costs of documentation, clinical documentation, other places where anywhere that you have to do a language task, whether it could be just searching and mining, piles and piles or millions of documents to get an answer, or writing volumes and volumes of content. It's a great opportunity to use generative AI. How do you improve engagement? Like, can you actually have a human-like interaction paradigm with your constituents, with the employees, patients, physicians, any of that thing? That's another opportunity for it. And then generally, it's a good, I like to call it, I'm going to coin this thing called first mile problems and last mile problems later on in the presentation. But it's a good way to get started. If somebody is stuck, you have a writer's block, you don't want to actually write a page, the AI co-pilot or the ChatGPT kind of a companion is great to get started, to brainstorm, to ideate, if you will. So it kind of helps with creation, if you will. That's a big theme around here. Okay, so with that, let's get into part two today. So we talked about, these foundation models briefly, right? But I want to spend a little bit of time going into this, right? And the foundation models are nothing but, these are classical techniques that you have, language tasks, like understanding, reasoning, named entity recognition, or relation extraction from a sentence, or just being able to understand what a piece of language mean. Like, we live in a world, and I probably mentioned this last time too, where we say the feet runs, the feet smells and the nose runs, right? That's the way we humans speak. I mean, imagine, like, it's technically not accurate, but it's figurative speech, right? The nose is supposed to smell and the feet is supposed to run. But then as human beings, the way we have evolved language, we automatically understand what that means, right? Well, the big breakthrough that happened is using that techniques to understand the nuances, the figurative speech, all of that stuff was now possible using these thing called foundation models. And foundation models are based on a few basic architecture. The most common one, or the most popular one that is based everything that we have done so far, is the transformer architecture. Google launched it in as late as 2018, I would say. 2017, I think, 2017 was a paper. The paper was very aptly titled, "Attention is All You Need," right? And then what that went into do is actually it spawned the evolution of all the different things. And I'll show you a view of how large language models are actually getting developed and spawning out of that particular thing. But that core innovation led to what we call foundation models. So it's called a very popular foundation model is BERT, or bidirectional encoding reinforcement transformer, right? So it's basically it's an architecture that you use for doing things like named entity recognition, or understanding sentiment in a particular thing, all these language tasks, if you will. And what that led to, that BERT models led to, was a lot of those models got open source. A lot of people use proprietary data to train those models and package that weights and open source those models so others can pick it up and run with it. It just opened up a whole suite of innovations. And then the big thing that happened was the GPT and the GPT-2 and 3 that happened. And the bigger thing, if you look at this trend, this is from, I think it was from the Economist article, but the huge scales of data that you could throw at these things created something very interesting in these architectures. It created the ability for the models to learn new things that humans will never scale to label and tell them. These are all what we call, self-supervised or unsupervised models, wherein you're not telling the models explicitly how to think about things. You just are feeding them a bunch of data. This is not scalable to do it. So the big unlock that happened, you see in this cluster here, was this huge scales of data on classical techniques. It created this evolution of these models to be, generally capable across a wide variety of tasks. What does that mean? What that means is now we have, when you go to ChatGPT and you have no history with ChatGPT, ChatGPT does not understand or know anything about you or your data set, and you ask a question, and the holy cow response that you get is this out-of-the-box experience AI. And I'm going to make an argument to you saying, well, that while that is amazing for a consumer-oriented approach, in enterprises, when things get more real and more complex and more hairy and more domain-centered, that may not be the best approaches to do it. So foundation models. I talked about this slide last time too, but this whole notion of these large language models enabled this new interaction paradigm. And I'm just double clicking on that, right? What it really means is, like, you have these models that understand human language in the way you can ask the model. So all of a sudden you had, think about, 5 years ago, 2 years ago, a year ago even, you have to write, if you have to build a system to let's say, do named entity recognition of text or image recognition, in an image, find different objects, object recognition within an image. Well, you had to get your Python libraries, you had to set up your Jupyter notebook, you had to write everything, you had to write code in Python, you have to learn the syntax, you package it, you take the data, you train it, you label it, and you retrain it, you deploy the model, create an inference endpoint, and then use it. So look at the time delta it takes. Today, the language models, the power that it encodes is you can just ask a model like the GPT-3 or a llama or any of these things, a general question that you would ask of the data saying, here is the data, find me the objects that I'm looking for in this image, or find these entities in this body of text. And you don't have to learn coding. You can just talk in English. You can just give the instructions. And the models, the algorithms have, the layers have the capability to understand that human language. That is the big unlock here, right? So the flexibility to use human language or English as the most popular programming language in the world and the universe today. That is a big unlock that happened here. What it can translate to, and it's already translating to, is to, in the world where you have this data that exists in multimodal ways, it could be text, it could be, in healthcare claims or financial data, public databases, research and literature, voice and, recordings, if you will, ASRs, or imaging, all of that, you can actually take all these algorithms. Not everything is capable across all the modalities, but we're going into a world where these multimodal algorithms can use human language as an interaction mechanism to pass information, insights, reason, compare against these things. So the workflow, the process that we see is all of this gets extracted and embedded as a dynamic multimodal knowledge set. It could be a knowledge graph, could be embeddings, could be a combination of the two. And then using these large language models, you can deliver different multidimensional experiences for the users and constituents, right? That is why we're all talking about LLMs today. This is a huge shift in the market, right? Now, let's get a little bit more deeper here. The LLM market is evolving very, very fast. I mean, if you take a digital detox for 2 days, you come back, you would have completely, we lost track of where we are in the AI market today. It's that fast, right? So there's a bunch of companies, there's a bunch of tools, a bunch of models, there's closed source, there's open source, all of this coming up. But the best way to think about this is in two different ways. Technically, there is different architectures, right? So the encoder-only models, BERTs, which still, I believe, at least now in a real case and enterprise use cases, are more popular and still than the GPT models, which are decoder-only models, generative models, if you will, or a T5, which is a Stanford model, which does that. And then there's two ways you actually do it. The modeling tasks are either using a mass language modeling or a causal language modeling. These are all you don't need to understand the technicalities here, but there are different techniques to use that. The other way to think about this is the business model these models have. A lot of them are black box APIs, right? The GPT-3, 4 from OpenAI, AWS's Bedrock, AI2 or Allen Institute's Jurassic, the Google Lambda, or the MetBomb 2, all of them are black box API. You have no idea what's going on. Now, they give you some levers to, fine-tune that model with your own embeddings and your own data set. It is very expensive and it's hard to maintain, let me tell you that. But these are black box APIs that are extremely capable across a wide variety of generalized tasks. When you get to narrow tasks and stuff, that's when things get a little concerning. The open source models, on the other hand, are the ones like your BioBERT, your bioclinical BERT, clinical BERT, MedBERT. There's all these different BERT, bidirectional models, BERT models. So they're extremely popular, extremely flexible. You can modify it. You can apply data-centric AI development practices to that, to model your data to that models. You can fine-tune it, change the attention thing. A lot more flexible and very useful for these, narrow, enterprise level use case. There's a lot more newer ones that are also broadly capable, like the Gatortron, the Biomegatron, if you will. It's an NVIDIA actually came in, or MedAlpaca. All of these models are open source. Some of them are GPT generative models, BioGPT from Microsoft, for example. But there is a wide variety of it. What does that mean? Well, the big fundamental question you have to ask yourself, and we'll make this all real when we talk about use cases, is to LLM or not to LLM, right? The Dartmouth conference in the 1960s, 1954, I think, was the summer of 54 or 55, is the most iconic conference that happened that, was the origin, birthplace of artificial intelligence, if you will. Researchers came in and talked about it. And there was one common definition everybody aligned on there. There was a lot of discussion, a lot of proceedings happened, which was that AI is it's a collection of techniques. It's a bag of tools for a bag of problems, right? A good friend of mine, Jaydeep Ghosh at the University of Texas, Austin, he uses this as whenever there is a conflict on saying we should use this approach or this approach, or is this the better model or is that model, we're saying it depends. It is always a bag of tools for a bag of problem. So the big question that everybody's having, every executive in the world right now is talking about using chat GPTs or large language models. Should we build our own LLM? Should we use an LLM? Should we use chat GPT? Should we use our own this thing? The easy or the accurate answer here is it depends. So I put that into a 3-point framework, right? One is the problem fit. So there is first mile problems and last mile problems. Think of first mile problems as consumerish use cases, search, chat, engagement, where your experience that you're trying to deliver is more critical, more important than accuracy or correctness of the responses. If you search Google for saying, get me the best Chinese restaurant, the reason they're able to get away with posting an ad on top that was probably paid by an Indian restaurant selling Chinese food, and that's going to pop up first there because they paid for the ad, and they're still okay, and consumers are okay with it because it's a first mile problem. You're not looking for accuracy. You're looking for experience, the frictionless behavior, and so forth, right? So get examples of search. Search is also relative because if you're doing information retrieval of specific things like, clinical data, and you're looking for, value-based care, risk adjustment measures from clinical data. Well, you can't do a broad thing and give you keyword responses. You got to do more narrow stuff. But that's first mile consumerish kind of problems. And I didn't coin those terms. First mile and last mile problems are actually coined by a gentleman by the name Chris Ree. Quite recently, he is a co-founder of Samba Nova, which is a silicon company that is building hardware for AI inferencing and training. And he's also a professor at Stanford. So, and he talks about this thing. LLMs are broadly first mile problem solvers today. Right? The last mile problems are the ones that we're more familiar with, the more understood. That's the very, core to what we have been doing in the world of AI all this while. Your prediction tasks, your document understanding tasks, the risk measures that I give you an example of, where your correctness is more critical than the experience you're trying to deliver. I mean, of course, experience is also interesting because AI always had an adoption problem, right? Which is what these first mile problem problem solving solutions like LLMs can solve, right? So this is a very important distinction. So picking the right tool for the right job, for the right use case is probably the most important thing you will do when you're deploying or thinking about deploying AI and LLM in your enterprise. The second thing, and I'll give you a deeper framework to talk through, if you're looking for prototyping, so generally, if you think about these general models like GPT-3, they're broadly capable. They're, mile wide and an inch deep, right? Now that inch is actually a very, very deep inch. It's probably 100 miles or top billions of miles wide and hundreds of inches deep, but it's not deep enough that you would get with a last mile problem solver like a BERT model, if you will, right? So one thing to understand is the foundation models, LLMs, are still very nascent technology. It works great for POCs and pilots and stuff. It is also displayed for, if it's a first mile kind of use cases like customer engagement, chat, or any of that stuff, it has been demonstrated in the last 3 to 4 months, which in the IT landscape is not that long a time. It is demonstrated that can actually survive and work very well in those cases. The core use cases that has to handle large volumes of data and veracity is an classic enterprise problem. What we are finding, and we do a lot of work with several large payers and providers, and we're in healthcare, but we also worked in other industries too, in pharma. When you're trying to put in like 36 million patients' records through a particular engine, a GPT kind of model really, it becomes really hard for it to handle because the amount of pre-processing and stuff that you have to do, and then you get this broad capability. The other interesting, the funny thing is if you think about like let me hold. I'll get to that particular thing about an NER example that I have, like a named entity recognition, how a generative model like GPT will handle that question versus something like a BERT model, right? So the last factor is about cost. LLMs are very expensive to run, fine-tune, train, and think. Now that said, very GPU intensive. That said, the evolution is these large language models become a foundational infrastructure, just like we would use an Amazon EC2 instance or a Microsoft virtual machine for Azure virtual machine to actually build your applications. these LLMs become a foundational infrastructure block that you can build applications on. That's the hope. That's the way, you know, Microsoft is pushing. That's the way, you know, all of these things in there. But I'll say the LLMs we have today, which is just the GPTs of the world, really good first mile problem solvers, not that good in the last mile problem solvers. I'll give you some examples of that. And then so smaller models that are easier to run, train, fine tune, and relatively cheaper to run because the amount of GPU and stuff is something that we're still seeing more. The more enterprises are going to continue to adopt more smaller models. The big opportunity, however, that we are actually pushing for is, I think this is not an either or problem. This is an and problem, right? Being able to match the right solutions for the right problems is going to be key in how we do it, right? I'll give you a few examples of these are actually published data that's I'm taking from. There's a couple of very recent. This was published in 23rd of May. This was revised. It was submitted there. It's actually just was revised yesterday. So very new paper coming out. It's in review. And there's a lot of research being done saying ChatGPT, for example, it's a jack of all trades, but master of none, right? You're actually realizing, so there's a notion called few shot learning, which is with very few examples, you can get good enough on a particular task. Or zero shot learning with no examples, ask a question and give me the answer. ChatGPT or these GPT models are terrific at that, right? But when you're actually trying to do a more difficult task, like for example, these two came from a different paper called Does Synthetic Data. It's a different paper, but it's called Enough These Things. You see the difference in the performance or the thing. So NCBI disease is basically a corpus of data where you have a lot of text, which has mentions of different diseases and conditions, right? All those nuances on it. The state of the art of actually using that for precision recall or an F1 score is in the 80s, like 80% accurate when you're about finding something 90%, almost 90% of the time, you're not going to miss anything. And 86% or 0.86 probability is the high, 86%. It's very, very accurate to go do it, right? That is state of the art today. ChatGPT or these GPT models are like 40 to 60% lower than that. There's also John Snow Labs also did some deep research on this on specific things. BC5, and all you're doing here basically is identifying a word and saying that word is actually means, let's say there's a adenocarcinoma. Well, adenocarcinoma is a disease of this class. You're basically doing a classification by identifying, it's called named entity recognition, and you're classifying what it is. Just a simple task like that, which is, it's not technically simple, but it's simpler than, writing a whole page of, a new blog, right? But ChatGPT and these models behave very terribly on those kind of things. BC5 CDR is actually a chemical, this drug causes this side effect. So understanding in a sentence that those two words are related and what's the relation between them, see the difference. It's about 7% accurate when you use ChatGPT, right? 7% of the time, it actually could find the particular thing. Similarly, for relation extraction, there are different data sets and so forth. The point I'm trying to make is when it makes sense when you think about it. How does a model like an NER model, like your state-of-the-art model, like a BERT model work is you read the sentence, you understand the words, it's got knowledge of these words may mean something like this. So it is going to extrapolate that and find, okay, I'm looking at this word, and then I'm going to give you, that this is of this particular class. It's just doing a very simple classification thing. A GPT model, the way it behaves is I'm oversimplifying this. It looks at the word, it identifies it, it says, this probably is a disease. It may get that right, but then it doesn't stop there. It actually goes and does another prediction of, because end of the day, GPT models are a glorified autocomplete model. It has to generate. It cannot give you the answer as is. It has to generate the answer based on the knowledge it has. So by the time you may do a good task of identifying the word and the disease, but then when you translate it and give it back to you, it adds another layer of probability, so the performance drops, right? So it makes intuitive sense when you think about it. What does this mean? Here's a simple, framework that I learned from Alex Ratner, who is a professor at University of Washington. And the simple way to think about the XY chart is like on the Y chart, on the X-axis, it's on the left side is prototypes and pilots, and the right side is production, enterprise ready kind of thing. And he was making this argument about out of the box AI, as we talk about, it's not going to work for enterprises. And I completely agree with this. And on the left side, on the Y axis, you see generic tasks or complex models or domain complexity to very bespoke, very specific problems that you're trying to do. Most common enterprise applications reside here. They require you to have very high quality of data and knowledge of how this thing, so you can kind of course correct and train a model to go solve that problem. Most of the problems the ChatGPTs of the world solve is down here, which is what we call now the AI that works out of the box, right? Which is great for generic problems, also for prototypes. If you build these, production quality systems for these generic problems, and there are massive, great examples like Jasper AI or, Copy AI, all of these companies who are actually building this. Like, you want to create a Facebook post title very effectively, highly fast, and the marketing task, which doesn't require you to have domain knowledge. Those models are really good generic, but they've done it and built the enterprise scale kind of capabilities in it, being able to support hundreds of millions of users and deliver the sub-millisecond response rates and so forth. That becomes a commodity capability. So it's a simple way to think about it, where we believe that the opportunity is not to go and say, like, I'm going to pick ChatGPT and so forth. I think as enterprise, you got to think about, like, what is your large language model strategy and stuff. And my recommendation is actually to use, focus on those core complex applications, and then focus on building and curating high quality data and knowledge, because that's the defensible moat in this thing. Doesn't mean these at the bottom does not work. It has to work, and there's a lot of low-hanging fruit to do that. So to select an LLM strategy, there's a few different things that I want to go, and then I'll go into use cases, I promise, right after this, right? So focus on the use case, security, industry, readiness, and fit, and so forth. If you're using a domain-trained LLM, which we recommend you do for healthcare, your use cases like chart abstraction, summarization of charts, right? You send a medical summary of a chart to ChatGPT, like from this thing, let's say it's anonymized, and say, summarize this 200-page document for me. One, it's going to cost a lot of money. Second, it actually, let's say it summarizes it, versus you have a very domain-trained LLM that's BERT-based, or even like a GPT-based, but like very much pre-trained with biomedical corpus and clinical data set. That's going to perform a lot better for those kind of tasks. It's still a generative task, but then using a domain-trained thing, right? So you've demonstrated much better performance for all the clinical benchmarks, and benchmarks don't mean anything in real world other than the fact that you have a common set of widely acknowledged and agreed upon data set that these models are pre-trained on, right? And it's important because, otherwise you don't know what these models are trained on. When you actually want to have, deployment flexibility deployed in your environment, smaller models, it's not going to be billions or hundreds of billions of parameters, anywhere from 100 million to, like, we even have a model that's like probably has, a couple of million parameters, and it outperforms everything else out there for a specific task. It's a very specific HEDIS risk measure abstraction from charts, for example, right? And so, but that's all you need for to solve a particular problem, right? And then you have these much larger generalized LLMs, 175 billion and more kind of things. And it's like this, there's going to be a race of doing that, because this really captures the general applicability. I mean, this is the whole notion of AGI, artificial general intelligence, is actually is a research task of trying to build a large enough, broad enough single model that is generally capable across all tasks, right? That's why you hear people saying, are we at AGI versus not? Because these are all paths leading towards it. We're nowhere close to AGI, right? These are very good for general tasks that can be learned on the fly without much examples. These are often black box models, difficult to integrate things like explainability, security, privacy, and so forth. It's generally more expensive to fine tune and maintain for private data sets. And then last thing that you have to think about is the enterprise readiness, robust embedding and encoding strategy with private data set. Your data goes back to the basics. Data becomes all the more critical, focusing on curation, transformation of that, pre-training it, fine-tuning, and getting that data to a point that can really uniquely highlight your knowledge and data to power these powerful models to actually deliver value for you. That's going to be the whole thing. And then future, you will want to have the flexibility to swap out these LLMs, right? If you start with GPT-3, GPT-4 right now is the best performing state-of-the-art LLM today for common tasks. MedPalm 2 is probably, arguably, one of the best performing models for healthcare and biomedical tasks. And we have a feeling in it, that though there might be a new company that's going to pop up in a few years or a month or 6, 8 months who will have a better performing model because they focused on getting the right data. They, did the right reinforcement learning with human feedback and so forth. But if you're an enterprise, you're building applications, and most of your IT folks here, you don't want to keep writing and rewriting APIs to use different models, right? So you want the future proofing and so forth, which is, I'll have a plug for what we do at Autonomize, and these are the problems that we try to solve for. So let's talk about a high-level cheat sheet for use cases. And we're about 2 or 3 slides out before we wrap up, so I want to make sure that I have enough, at least 10 minutes or so for questions this time. One is, if you're doing clinical documentation, so the way I've actually looked at it, saying, is LLMs the better fit for these kind of problems, or is it a smaller, more fine-tuned model a better fit for it? If you're building documentation, I would say LLMs are best for you because it's a generative task. So the wider the model, it is going to be better at generating human-level content, the broader the model, right? That said, there's going to be some work in there to actually, you can use it for transcribing, you're digitizing your doctor's notes, summaries, clinical documentation. Like I said, I know it's a huge focus across the industry to lower that 70-60% of the time that our physicians and caregivers spend in documentation. Can we deliver that? Yes, I think there's a huge opportunity here. There's nuances, there's things that we have to actually understand. You start realizing, if you look at all the documentation, 80% is duplicative documentation, right? Every time a patient comes and visits, there's a bunch of data that's copy pasted and it's all wrapped into the next note, the next note, the next note. So you have to do all of that pre-processing work to clean that up, make that decent before you can actually feed into these large, powerful LLMs. Otherwise, it's going to start making erratic recommendations and so forth. Medical information retrieval, a glorified way to say search, right? If you're using it to mine large, usually publicly available research and literature, which means if it's publicly available literature, chances are your GPT-4 is already trained on that, right? Like if it's a clinicaltrials.gov or PubMed's publicly available 30 million documents, all of that, 30 million papers, all of that is abstracts. They're all probably trained on it. So it's really good for very quick. You can actually create a little bit of fine tuning on a particular task, work out the prompt engineering, and immediately you can see value if somebody's just looking for what's the latest research on hemophilia, and give me the top 10 reasons, top 10 drug launches that happened to support this in the last 10 days, right? So if you have access to internet, so bard.google.com and stuff, it can be very powerful to do that. Patient engagement, for virtual health assistants and chatbots, providing almost human-like, back to my point on experience greater than accuracy. There is a double-edged sword here when you're using it into patient-facing things, which is all the news that is making, where you might get into situations where it's giving wrong advice. But there are ways to actually guardrail these experiences through smart embedding strategies and so forth, reduce hallucinations, and a lot of different things. But that is a great use for it. If you're doing clinical decision support, as long as you're using it for knowledge retrieval and reasoning, right? I have 5 different documents about a particular patient. There's diagnosis, reports, there is lab reports and so forth. I want to just go do a reasoning across that thing. LLMs potentially will be a really, really good aid tool for the thing. And the big opportunity, because of my point on its experience greater than correctness, all of these things that you use LLMs are best suited for only suited for a human in the loop kind of a workflow. Doesn't mean that you can improve the workflow, you can compress the timelines and reduce costs and administrative costs. But if you don't have the human in the loop and you're using GPT-4 to actually make those decisions, chances are it's not going to be accurate most of the time, right? And I think a lot of the time, and that's going to be a huge issue, right? Medical education is another use case. The flip side of this is when you're going more narrow and more deeper and more, things like, hey, I want to understand the chart abstraction. So I want to do the same problem that I did earlier. I want to get all this thing, but instead of documenting and creating documentation, I want to understand how is my population doing for these HCC risk adjustment scores or your HEDIS scores and measures and submeasures. Well, that is an act of actually identifying different entities, information retrieval, getting accurate about it, high level of degree of confidence. You may still use it in a human in the loop kind of framework, but you need powerful, narrow models that does that, rather than a broad model that'll just pick everything that, if you're looking for a HEDIS measure like COL, You don't want it to be picking up things that everywhere you have a mention of colon, instead of saying colon, it's going to find that out as colon, and it's going to start pulling it up. And so those kind of challenges you'll run into if you have a broad model. You just want specific narrow models. Image analysis, a great example. There is a lot of things, although there's a lot of research being done, can be used like a diffusion-based models, like a DALIs of the world, or GPT-based DALIs, or like diffusion-based, like stability AI, stable diffusion, and Mid-Journey, and so forth, to build like, synthetic digital twins of the original data, and creating in a variant. So kind of controlled way to actually build synthetic data. There's a lot of those used there, but if you're just looking at analyzing medical images, your CNNs are going to be a lot more performant than a large language model. Predictive analysis for everything from time series, or what we call the LTSM kind of problems, simpler problems, simpler models like statistical models will suffice for doing that. Genomic analysis, data interpretation. Actually, it's a really hard problem, genomic data interpretation. It's because it's sequential, it's time series, it's all these different things that come in. LLMs are terrible for doing that today, right? Same thing for anomaly detection, understanding all these different things. And you'll have the slides, and I'll send this to you. But I just wanted to give you a view of there are ways you can solve the problem, and the answer is never. Most likely we all have been in, it's like we talked about this during, I'm trying to find an analogy still, I don't have one yet, but, we went through other parts of the industry where you don't use the same tool for all the problems. And the problem with a very hyped environment is everybody will try to use the same tool for all the different problems. So what can we do about it? What are some key considerations? I would say absolutely embrace and experiment with all of these out-of-the-box algorithms. But the focus is to learn, gain exposure. But then what you really want to do is build your own UGPT, as we call it, right? And to do that, data and knowledge are the best long-term modes for your business and for individuals. If you're a subject matter expert in something, you're going to be all the more valuable in the world of LLMs than an LLM that's trained on that subject matter, because the LLMs we're not there yet where these systems are capable of having deep domain knowledge in any one thing. Pick the right tools for the right problems, like we talked about. Not all problems require LLMs. First mile versus last mile. Prototype versus production, cost, and so forth. I re-emphasize this thing about data-centric development, which is huge. If people who are in data science and machine learning have realized this over the last, 3-4 years. The big shift that happened ever since like 2019, 2020, maybe even, is this notion of, earlier you used to actually get a sample data. If you go to a Kaggle competition, it's just you have a data set, and the data set doesn't change. You just have to build the model, parameter optimize, you do feature engineering of the data, you deploy the model and stuff. You're all about building the model, right? That world is gone because you don't need to build a model from scratch. You have these LLMs, foundation models, things you can pick from. So now you have to shift your focus back into the data to see, do I have the right data? Can I clean it up? Can I have enough diversity of it? And that systematically engineering the data used to build an AI system is going to be, you still have to work on the model, but that's not where you start. You spend more of the time here, right? And starting with the data you have, curating, pre-processing, encoding, getting it ready is going to be key. There's this notion of if you can capture human knowledge through reinforcement learning with human feedback or other techniques to train and fine-tune your models, that's going to be huge for you. We also believe that the future is hybrid, so it's not going to be one or the other. You'll have a lot of small specialized models, which are going to be much, much better performing than large generalist model. But these things, you should leverage it all. What I mean by that is look at this, pick the right tools for the right problems, the second bullet up front. And then it'll coexist and you should leverage this all. My last 2 slides is what we are enabling for several organizations like yourself is this, we call it the UGPT. We used to call it XGPT. It's not X, it's about, Kaiser GPT, if you will, right? How do you establish a context-aware, domain-optimized, personal AI platform to take advantage of all of these things? And that's what our Genesis AI platform enables, which is we abstract the complexity of what models you need to pick for what problems. We programatize that through prompting, chaining, model selection, model management, and so forth. So it makes it easy for your application developers to go build that out. Right now, we've launched several different applications on our platform, and in the process of actually transitioning into a platform-based view to help. And we focus on the data curation, normalization, structuring, embedding, the data security, deploy it within your firewall, PHI redaction, all of that stuff is where we actually focus on. So without much ado, I think that's the presentation. No, thank you so much for the opportunity. I enjoy those questions too. So thank you.
Thank you. We are past the time, and thank you all for joining us. And we'll bring you back next time for another session.